Hi guys, here's another video about the CSS Pure Mathematics Exam from 2023. We are still in section A and this is question 2, item B. So it says, suppose U and W are distinct four-dimensional subspaces of a vector space V of dimension 6. Find the possible dimension of U intersection W. So let us begin. So first, since U and W are subspaces of V, we know that U intersection B is not also a subspace of V, but it is also a subspace of U and W. Thus, since, for example, the dimension of U is 4, we obtain that the dimension of U intersection W is greater or equal than 0 and lesser or equal than 4. Okay? So now we have put the dimension of U intersection W in the range of 0 to 4. So until now, we know that it can be 0, 1, 2, 3, or 4. So now let's see that, in fact, it cannot be 4. So the dimension of U intersection W cannot be 4 because if we had this, since the dimension of U and the dimension of W are 4, we would have, and U intersection W is a subspace of both spaces, we would have U equals U intersection W equals W. But our assumption is that U and W are distinct vector subspaces of V. So we cannot have the dimension of U intersection W equals 4. And therefore, the dimension of U intersection W must be less or equal than 3. So now, until now, we know that it can be 0, 1, 2, or 3. So let's see if we can get rid of more possibilities. So now recall that when we have two subspaces of vector space, we can construct its addition, U plus W. In this case, we have the subspaces U and W. We can construct the vector subspace U plus W, which is defined as the set of all vectors in V of the form U plus W, where U is in U and W is in W. Okay? This is a subspace of V, and since V has dimension 6, the dimension of U plus W is less or equal than 6. And we will see that this is very useful. We only need to remind ourselves of this formula. The formula tells us that the dimension of U plus W equals the dimension of U plus the dimension of W minus the dimension of U intersection W. Since we know that the dimension of U and the dimension of W are 4, each one of them is 4, we get this 8 here. Okay? So the dimension of U plus W equals 8 minus the dimension of U intersection W. And now we get this 8 minus the dimension of U intersection W and use the fact that the dimension of U intersection W is less or equal than 6. So we get this inequality here. So 8 minus the dimension of U intersection W is less or equal than 6. Now we rearrange the terms of the inequality, and we obtain that the dimension of U intersection W must be greater or equal than 2. And putting this together with what we had before, we get that the dimension of U intersection W is either 2 or 3. Okay, now let's see what can we do with this information. As we will see, actually, both cases can happen. So in the situation we pose in the problem, the dimension of U intersection W can either be 2 or 3. So let's show that this indeed is true. So first, since V is a vector space of dimension 6, let B be a basis for this space. So B has vectors from V1 to V6 because of the dimension of V. And now let's construct subspaces which satisfy the hypothesis of our problem. So first, let U be the span of the first 4 vectors of the basis, so the span of V1 to V4, and let W be the span from V3 until V6. Okay, it's easy to see that the dimension of U equals the dimension of W equals 4. because since B is a basis, all these vectors here are linearly independent. And so the span is also linearly independent. Again, U intersection W, we can easily see that it is the span of these two vectors here. So its dimension is 2. And therefore, in this case, the dimension of U intersection W is 2. And we were able to find subspaces U and W of V of dimension 4, whose dimension of intersection is 2, and so it is indeed a possible case. Now let's see that 3 is also a possible case. So again, we get U as before, the span of all the vectors from V1 to V4, and now we get W as the span from the vectors starting from V2 until V5. Again, we have the dimension of U equals the dimension of W, which is 4, because these vectors are all linearly independent. And it's easy to see that in this case, then U intersection W is the span of V2, V3, and V4. So it is a vector space of dimension 3. And we are done. So we have showed that we have constructed subspaces of V of dimension 4, whose intersection has dimension 3. So this is also a possible case. And we are done. That's it for today. And I hope you like this video. Please subscribe, leave me a comment, and give me a thumbs up. I would love to hear from you guys what you think about the video. If you liked it, if you want more content, please let me know. Thank you very much.